Ever pondered how a feather falls slower than a stone, or why the planets circle the sun in such a precise dance? These are questions of movement and gravity that have stirred the human mind for centuries, leading us on a quest for answers that seem to elude our grasp. The world around us moved in patterns, a ballet of celestial bodies and falling objects, but the choreographer of this dance remained unknown. This enigma of movement, of why and how things move, stayed a mystery until the 17th century. It was then that a man stepped onto the stage of history, a man who looked at the world not just with curiosity, but with an analytical mind that sought to decode the laws that govern the universe. This man was no ordinary observer. He was a revolutionary, a game-changer in the world of science. Enter Isaac Newton, the man who dared to question the universe and its secrets. An apple falls from a tree, ordinary occurrence or a moment of revelation. Picture a young Isaac Newton sitting under an apple tree on a calm, quiet afternoon. Suddenly an apple dislodges from its branch and falls, not sideways, not upwards, but straight down to the ground. This simple, everyday event triggered a series of questions in Newton's mind. Why did the apple fall straight down? Why didn't it drift away or shoot up into the sky? This wasn't just idle curiosity. This was the birth of a profound insight into the nature of our universe. It was this moment that propelled Newton towards formulating his influential laws of motion and the law of universal gravitation. His observations and subsequent theories revolutionized our understanding of the physical world. And thus, the falling apple sparked the illumination of Newton's mind, leading him towards his laws of motion and universal gravitation. 3 laws etching the fundamental principles of motion. Imagine a world without rules. Chaos, right? But when it comes to the physical world, there are rules. Laws, in fact, that govern how things move. These are Newton's 3 laws of motion. First up, the law of inertia. Picture a ball at rest. Unless acted upon by an external force, it will remain at rest. That's inertia, the resistance to changes in motion. Next, the law of acceleration. This law stipulates that the force applied to an object equals its mass times its acceleration. In other words, if you push a heavy object, it takes more effort to get it moving than a lighter one. Finally, the law of action and reaction. For every action, there's an equal and opposite reaction. Think of a swimmer pushing off a pool wall. The force exerted on the wall is met with an equal force propelling the swimmer forward. In essence, these laws describe the relationship between a body, the forces acting upon it, and its motion in response to those forces. They're not just theories or abstract concepts. They're the rules that govern everything, from the way a soccer ball arcs towards the goal to the way planets orbit the sun. These laws, simple yet profound, govern everything from the smallest atom to the largest galaxy. Gravity, the invisible force that keeps us grounded and the planets in check. This force, as we've come to understand it, operates on a universal scale, thanks to the brilliant mind of Sir Isaac Newton. Picture this: every particle of matter in the universe, from the smallest dust mote to the largest star, is drawing every other particle towards it. This attraction is what Newton's law of universal gravitation is all about. But how strong is this pull? Well, Newton's law tells us that the strength of the attraction depends on 2 things. First, the mass of the objects. The greater the mass, the stronger the pull. It's why the Earth, with its considerable mass, keeps us firmly planted on the ground. Second, the distance between the objects. The farther apart the objects are, the weaker the pull. Hence, the Moon, despite being much smaller than the Earth, keeps us at bay due to its distance from us. But here's the kicker. This force decreases rapidly with distance. It's inversely proportional to the square of the distance between the objects. So, if you double the distance, the gravitational pull becomes a quarter of what it was. It's this delicate balance of mass and distance that allows the planets to orbit the sun without spiraling into it or drifting off into space. And just like that, Newton decoded the cosmic dance of the planets and gave us a deeper understanding of our own existence.